So what I want to talk about today is a new search for micro-EV. So this was Ben's sort of third area, right in the middle, right below the ADMX experiment, a new experiment that we're building. And so here's the group. So Saptarshi is the motivator and key guy putting this all together, right there. Roman Klevetov is a postdoc with him, and Joe Wiedemann, Nate Otto, and Joel Marie-Began are grad students on the project. There's another Dickey fellow, a postdoc, joining us soon, Frank Fu, and you'll see these components come in. And on the magnet side is because you'll see how essential this is Yuhu Zhai, who's here. Yuhu's back there from PPPL, so they're making our magnet. And then a key element is a really super sensitive readout, and Peter Day, right there, is behind all that. So here's the landscape in a little bit larger framework than what Ben showed. So here are the QCD axions right here. And then I'm an experimentalist, but I can say, right? And so string theory motivated axion-like particles cover all this whole range, all the way down, all the way up, and different methods are used for different bits. You can even use the microwave background at the very lowest masses. So let's and here a number of experiments. So let's zoom in on that region to show you where we're looking. So we are again. I'll come back to ADMX. We are right here. So here's ADMX. Haystack is just up there. Alpha, which we'll hear about next, is up there. That was the rightmost part on Ben's plot. So we're tucked in there, right below ADMX. And then we're related, you'll see how in a minute, to this larger family of DM radio experiments that are proposed and ongoing at this low end. So we're focusing here on 0.8 to 2 micro-EV, and that corresponds to 200 to 500 megahertz. And let me just point out here, abracadabra, because I'll come back to that. Ben mentioned that briefly. Okay, and I want to call out that this is, we're not doing this in isolation by any means. We just, lots of the group is part of the whole DM radio collaboration, and they're working on elements for that. I mean, just as an example, recently Roman and Saptarshi just built this cavity, coming back to the resonator question, with a Q of 2 million at 250 kilohertz, which is key, developing quantum up converters with Stanford, and then testing readout sensors with Stanford. So this part of this whole DM radio program. And we have had enormous amount of advice and interaction and help from ADMX and just all these side conversations. And we were up at Yale a while ago talking about the haystack experiment and learning lots of things. So it's not in isolation, and we just want to say we've benefited enormously from these. Okay, so here's the idea. What I'm going to use is actually a paper from Yanni Kahn and Ben Safdie and Jesse Thaler on this is the one that when I read it, I said, oh, wow, this looks so cool. I should try to do an experiment here. And I love this idea because it separates out all the pieces. So so the idea is if you make a toroidal magnetic field, it's DC, that's the key. And now that field interacts with the axion, as Ben was showing. Okay. What that makes is an AC field, AC current, pardon me, that's oscillating at the frequency, E mc squared equals nu, corresponding to the axion mass. That oscillating field there, then it's a toroidal, field, it's a toroidal current oscillating. It then makes a B field like this, right? And then you just put a B field sensor in the middle. Okay, so those are all the couplings. So we don't do this. I think the DM radio experiment is building something very similar to this and abracadabra. But that and we just sort of fold all that together in a cavity, as you'll see. And this is just from that paper, the current levels. If you go back, let me just get them here. And this is what, you go from theory units to lab units. At 10 to the minus 12 coupling up there in 1 Tesla field, 10 to the minus 12, it's a 1 Tesla field, the QCD axion will make a current that's about 10 to the minus 11 amps per meter squared, right? Which is, you can buy a Keithley current meter to measure, right? So it's completely doable. Of course, we're pushing beyond that. Okay, so what are the building blocks for us? And so this all comes back to early 80s paper by Pierre. So it's a Srednicki heloscope. And so it's a passively cooled superconducting magnet. And that's where PPPL comes in. I'll show you a picture of that. Microwave cavity. So half a meter cubed, cooled to 40 millikelvin. And then quantum noise limited amplifiers. As quiet as, we'll keep working down. And this is with Peter and colleagues. So where are we? So we've been working on this now, like all of you, for 2 years. So here's how we're pulling this together. So you can imagine a table right under there, a little table. So it's tabletop experiment, right? But here's the overall cryostat. So the magnet would sit down here. These are cooling. We've actually built prototypes of that. So it's a way to cool the magnet. And then a dilution refrigerator sits in the top, and sort of the business, the microwave readout system sits in here. There'll be a few pictures. And what we're doing is paralleling the development. So this mates together, but separately the bottom comes off, so we can build the magnet and test it in there. And there's a separate bottom for the top half, so the dilution refrigerator, so we can test the whole resonant cavity and all the cryogenics. So this is all designed and ordered and should be here in sort of January timescale. So we're here down in the lab. So so here's a breakout of this. So here is the final one. So the magnet is that blue element right there, and it's cooled with pulse tube coolers. Here's the cavity, which sits inside, and I'll show you more pictures of that. Here's where the electronics sits, and then here's all the cooling sits up top there. So let me just now walk through the 3 pieces. So again, here's the magnet. Here's the design. This is from Opera, and you can, it looks like it works. We will have our first design review near the end of October, and then the manufacturing review in January. And then looks like we can get it before the end of next year. But it's about 1 meter, cooled by 2 pulse tubes, niobium titanium, and there we are. So this is Yuhu's design. And the sort of things we're just dealing with and solving is, how do you run a pulse tube in a large magnetic field, and a DR in a large magnetic field, and all that sort of, and amplifiers in a large magnetic field, all that sort of thing. So to get a handle on this, because the magnets are so challenging, we built a 1/4 scale model. So there's Joel, but initially we were going to do this with niobium 310, and decided against that, sort of based on what the issues we ran into in this. We switched to niobium titanium. But anyway, here's our 1/4 scale model. So we've done things like we've gotten 600 amps down to 4 Kelvin and back, like keeping everything under 4 Kelvin. So that was through everything we'll use in the end, through copper leads and BSCCO and Rebco and all the, making all the transitions, all the joints and things like that. So we know how to do that. We can get the cryogenic performance we need. And this was one of our satellites for the big experiment. And at PPPL, the winding and annealing, the vacuum impregnation it's all built and ready to go. So in a couple of weeks, we'll take that over and actually wind that coil and then heat treat it. Okay, on the cavity, here is, I will show you a picture in a minute, but goes back to the resonator question and what the haloscope had in mind. And so we're not using that nice toroidal geometry, which separated all the functions so easily. For now, we use, it's a resonant cavity, very much like ADMX. And you change the resonant frequency of the cavity by moving a tuning rod around. And I'll show you a picture of ours in a minute. And what we're looking for, right, the signature of this, is, as Ben was saying, is a line. We're looking for a line, and we want to get down to the noise floor. We're looking for a line in the middle of that. And so here's an example of the line within the resonance of the Q of the cavity. So we scan, and you can see here that the scan rate, the ability to cover the frequency range, it goes roughly like the square of the energy density, so B4 V squared. That's a coupling, that's the Q of the cavity, and that's the amplifier noise. So we want to, you want to concentrate on all those, but it's especially sensitive to getting a high magnetic field. And so that's the idea. So then we tune across that. Okay, so here's the cavity. Full-scale prototype is built. This will fit in the magnet that Yuhu has designed. The tuning rod will go in later this month. And we've divided up our full search range into 3 sections. They'll have different cavity configurations, but the first is we'll do 380 to about roughly 500 megahertz. So this is being built. Here is, we've found a way to make a cavity for about just 6K, which is good. There's a model and data in there, so we're modeling this thing to wonderful precision, and it all makes sense for those who have worked on ADMX. Here's, we're following in many of the same footsteps. This is a plot in which we took the cavity, or Nate did, drilled a whole bunch of holes in the top, pulled up a bead from the top to the bottom as a function of radius in the cavity to look for the shift in resonance, so we could make sure we were mapping out the right mode, and then averaged over that whole height, and then fit it to the model. So you can see, and you can see delta frequency from the delta from our 350 megahertz resonant is really small. So we're making really precise measurements of the shape of the mode. So this is all going very well. The tuning, this is just a very preliminary picture, but that's what it looks like. There's the tuning rod sits in there. This is the axis about which it spins, and as I said, that will go in. Things we decided, I think other groups have moved their tuning rods with cold piezoelectrics. We are going to try to run it at room temperature all the way down. So I think we can make that robust and monitor the position of the cavity readout. And again, we're going to build all this to scale warm, and then put it together. So we're pretty excited about that. Okay, and then the readout. So we've built a bunch of testing systems. So this is Joe here, and Satarchi's commissioned, and with Joe, a whole separate cryogenic system, so we can test all the electronics in parallel. So when we get the big system, they all go together. So this is Joe working on that. And then this is an amplifier from traveling wave parametric amplifier from Peter Day's group, and tested in Subtarshy's dilution refrigerator. And it looks like we can, these TUPAs have been mostly used at higher frequencies, but they showed that in particular, this Caltech design, we could get amplification all the way down over the band that we needed. So this was really neat, and this is ongoing. This testing, fabrication, we're getting that loop going. Infrastructure, because all of this started, all this building started when the award started. So we've had to develop a bunch of things. One of the things I found, we couldn't use any, cost and time and quality. We've been developing our own coax. So this is Joe Wiedemann's. Joe is Joe Axco now. Just to get these reflections down in all these systems to enable the sort of readouts that we want. And along the way, developed, this is with Roman and Subtarshy, this new heat switch with pyrolytic graphite, which is really cool. We chucked out a whole bunch of gas gap heat switches. And we now have these 4 systems running in the lab. So we're cooling the magnet with this one. We are testing amplifiers with this one. We're testing amplifiers with the DR, and then this is another separate system that we're testing the resonators. So all of this is really coming together. It's hugely exciting. And lots of fun for all the reasons Ben said, and just because these are fantastic techniques. And then we've had a bunch of student involvement from senior theses to summer students to, so Princeton, we have these, these are all theorists, right? All theorists have to do an experimental project. So it's just an 80-hour project, and some of them end up loving experiment, and some of them appreciate what experimentalists do, and some of them just get through it. But anyway, they're all great and lots of fun to work with. And so everyone here has contributed. Let me stop there. Thank you.
Very much.